Good morning, good afternoon, and good evening. Welcome to webinar on millimeter radar and technology and related product design. Yeah, I am the presenter, Selva, and I have the panelists, Alagapan, who specialize in hardware, Srinivasan, specialized in firmware, Karthik is specialized in software, and Raja, who is specialized in application development. This seminar, the webinar is going to be about 40 minutes. The first 30 minutes is going to be the technical presentation, and the last 10 minutes is going to be the question and answer session. You can post your questions to question and answer module. One of the panelists will answer to your queries, and the last 10 minutes it can be a live question and answer session. So the objectives of this webinar is to brief the radar technology and the products using millimeter wave technology and related markets, and we'll be briefing, getting a little on the challenges in designing millimeter wave products, and finally the Mistral offerings on this technology domain. Let us get into the concept. If you see the radar, obviously there's going to be a radar side where you have transmitters and receivers, and the angle where you want to view the object side is going to be targets like the aircrafts or the objects, human beings, different targets. So the transmitter transmits radio waves towards the vicinity where you want to monitor, and the radio waves is reflected by the objects, targets. Can be multiple targets. The reflected wave is received by the receiver, and the received signal is processed further to identify the objects, like what range the object is and what speed it's moving and what angle the object is located. And there are multiple radars available in the market based on the applications and use cases. The types like radars like Doppler radar, synthetic aperture radar, and frequency modulated continuous radar. That's the radar we are going to discuss today. And monopulse radar, passive radar, planar array radar. These are different types of radars available in the market. So what spectrum we operate in millimeter wave? This is much higher frequency. From the name itself, is the wavelength is millimeter, and the frequency spectrum is 30 gigahertz to 300 gigahertz. That's the millimeter wave spectrum. There are other radars, is L-band, S-band radars operate on 3 gigahertz, 6 gigahertz, and X-band about 10 gigahertz. There are different radars, military radars. This radar, millimeter wave radar, specifically operates the lower wavelength. That's millimeter wave level, and operates at 30 to 300 gigahertz. So let us get into the modules. What are the different modules in a radar chipset? Like synthesizer. Synthesizer its job is to generate the frequency modulated continuous waves. So it generates called chirps. The chirp is nothing but frequency, sine wave frequency, and it's varied with respect to time. The linear varies linearly varies with respect to time. In terms of millimeter wave, the frequency starts 60 gigahertz or 77 gigahertz, and the frequency linearly varies with respect to the bandwidth. Suppose we have 4 gigahertz bandwidth, and it starts from 60 gigahertz, and the chip varies to 64 gigahertz. So you can see here, here this waveform, is a 4 GHz bandwidth. The chirp varies linearly with respect to the chirp frame. And the chirp has been transmitted. The chirp waves, frequencies, continuous waves transmitted or transmit antenna, and the reflected pulse from the objects is received by the RX antenna, and the received pulse is mixed with the source chirp, and the RX chirp is mixed, and the resultant output will be a intermediate signal, that's IF signal. If we have more objects, you will get more intermediate frequency signals. It's fed to the ADC, and the digitized data is further given to the DSP for application processing. If you see that TX chirp, transmit chirp, and receive chirp, you can see the phase variations. The phase variation is the delay of the chirp transmit delay between the source and the objects. That delay makes the phase difference. This phase difference in turn generates the IF signal. And the DSP is used to process the algorithms like the FFT and different algorithms to find out the targets. And if you see here, so this is the transmit chirp, and the received reflected pulse is plotted with respect to DSP process data. You can see multiple targets. So what is the specialty of radar? There are multiple technologies available to identify objects like a camera and ultrasonic, LIDAR. There are multiple technologies available. What is the uniqueness of mmWave radar? If you take range, radar gives much better range resolution because it operates on the signal flight time, and also LIDAR gives some level of accurate the range detection, and if you see the resolution from camera, you get much higher resolution because you're seeing the objects. What is an object identification? You can get the objects. And if you see the speed measurement, the Doppler shift, the radar gives a much bigger, much accurate measurement. And if you see the operating environments, the radar can operate 24/7 and different environments like the cloudy or nights, raining, different operating conditions it can work. And the size, if you take the size parameter, the radar is very small. It can be 2 inch by 2 inch, or it can be designed 1 inch by 1 inch based on the technology and antenna types what we design. And ultrasonic is also small. And if you take the cost, the radar gives it's the lowest cost. The product design based on radar is going to be the lowest cost. The camera based designs or LIDAR is going to be expensive. If you see the market where these radars are used, there are two areas. 60 GHz frequency range is used in industrial market, and 77 GHz spectrum is mostly used by the automotive market. If you take the industrial market, there are multiple use cases, different markets also into that area, where it can be used for occupancy detection or smart home, or gesture control in a house environment where gestures are integrated for TV operations. Already mobile phones has gesture based on mmWave radars. It's all already available in the market. Lighting controls, street light controls, secured windows, and an intruder. If some intruder comes, if you have the radar around your house, in front of the house, you can identify the intruders, and the flight control, collision avoidance kind of applications can be used. When you take up the automotive radars, basically there are multiple use cases around the automotive vehicle: collision avoidance, blind spot detection, automatic cruise control, and the multiple, many more use cases we can going to be seeing further. So what is the use case specific more use cases on the industrial side? So it's kind of building automation, gesture, robotics, traffic monitoring, security surveillance, factory automation, people counting, and occupancy detection. These are some of the applications, and it can be targeted to many more applications based on the users can use this technology. When you take up automotive domain, the use case is going to be around the vehicle. Suppose the radar can be mounted in the front bumper, or the sides of the vehicle, or the rear side for rear side, or on the doors. So the different use cases. The front side typically used for the cruise control applications, automatic cruise control applications, and the side from sideways is used for cross traffic alert, stop and go, or pre-crash kind of use cases. And the doors is used for obstruction detection. When you open the door, there is an obstruction, any object there, it will avoid avoid the accident or small damages. It will not open the door. Or then it can be used for the rear side, can be used for parking assist or lane change assist. These are some of the applications you can imagine around automotive vehicle. And the different radars, if you see the color codes, the long range, we use long range configuration of the radar, and then the mid range radars are used in the edges, and the doors we can use the short range. These are different kind of radar configurations we can do and use it. If you see the modes of operation, right? There are different modes we can configure the radars. Like up to 200 meters is called long range radar. And the medium range radars about 30 to 40 meters or 60 meters, the medium range radars. And the short range is about 20 meters. And it can be configured as ultra short range. That's about 2 to 3 meters, wherein you can measure specific the presence detection of passengers, or you can measure the heartbeat, the lungs rate. Those kind of applications can be used. So what are the different design aspects when we do the millimeter wave radar design? Obviously, you need to configure the radar to generate the right chirp waveforms. You need to configure the bandwidth, the ramp up time, the frequency, all the parameters you need to configure in the chirp. And you need to design the transmit and receive antennas based on the application. Like long range, the antenna pattern is different. And if it is a short range, the antenna, and you want a wider field of view, the antenna design is different. So this is going to be involved activity in terms of antenna design. And the ADC sampling rate, based on the IF signal, the ADC sampling rate can be configured. And the data processing. This is the larger area. You get a lot of multiple targets. What target you are focusing, what region you are focusing. It's going to be a lot of data processing is going to be there. And the process targets. You need to have a higher level application, wherein you can have the history of the application, tag an object, and track an object. The number of applications can be designed around the targets identified. So what are the different design challenges are involved during the millimeter wave radar design? As you see, this is a sample of the antenna pattern, and you need to select right antenna for your design. Suppose you are going to design the radar sitting in a roof, the ceiling of a room. So the antenna pattern is different. You have to have wider field of view and wider elevation, kind of full room you have to modify. Suppose if you are mounting in front of the vehicle, then the beam has to be narrow, to cover long distance. So the antenna pattern is different. So you need to select right antenna pattern for your design, and you need to simulate, do the patch design in PCB, and you need to simulate the antenna performance, how it's gradiating, how it's receiving the reflected pulse, and the right PCB material, because you are operating at above 60 GHz frequency range. You need to have right PCB material, low loss PCB material, to design the PCBs, and you need to really focus on manufacturing tolerances, wherein we cannot allow large tolerance so that your performance will get affected, or if you manufacture a large quantity, it may not be consistent across the products. And how to test? So because the equipments needed to test, characterize these antennas is very critical. The equipments are expensive. There are multiple ways you can test. So you need to decide, plan on what kind of lab environment you are going to test this product. So get into the antenna patterns and application. So suppose if you are mounting this radar in a ceiling, room size of 5 meter by 5 meter, then the antenna, the transmit antenna and receive antenna has to be designed in such a way that it occupies the complete room. It's not particular elevation. So this kind of antenna, 3 elements antenna in a L shape, it's going to cover the 2 antennas is going to take care of the elevation. These 2 antennas is going to take care of the field of view, and the receive antennas are placed in such a way that it can receive the signals all around the room. And suppose you are designing a short range radar, say about 20 to 30 meters, the antenna pattern is designed this way. And if you are designing a mid-range, we call this antenna as 3 elements, and this can give an elevation of 140 degree to 140 degree field of vision and 30 degree elevation, and this radar can operate up to 40 to 50 meters range. And the last one, the example is long range, where we call tapered elements, where the radiation pattern, what you get is narrow beam, where it can go longer range. This is an example here. We are showing a 8 by 8 antenna array. This antenna is suggested for a long range. You can see the radiation pattern, the 3D radiation pattern is going to be like this. The energy is focused in the middle. So generally the energy is going to get focused on the middle. That's how this pattern works. And the E and H plane curve is defined like this. Okay. The next one is let us see how we decide the PCB materials. We suggest to go with a hybrid PCB layer stack-up, combination of Rogers as well as the FR4 material, because the Rogers gives good performance on RF level, low loss PCB material, and the FR4 gives good manufacturability. So to have a consistent quality manufacturing and good temperature response as well as good RF performance, we suggest to go with a mixed layer stack-up. And the etching accuracy, the copper etching accuracy should be limited, should be within 10 microns level. And the wire drill and plating tolerance is very critical, and it should be limited within 10 to 12 micron. So what kind of PCB layers stack-up we suggest? Say hybrid layer stack-up. It's mix of Rogers. There are different Rogers material available, and also high-speed FR4 material. This is a typical 6-layer PCB layer stack-up for a single device, single radar device with the 3 transmitters and 4 receivers. If you see the core, the top core is Rogers material. The antenna is etched on the top side of the PCB. And the other cores, the inner cores, are FR4 material. This FR4 material is helping the manufacturability. And the other prepex are bonding material. They are FR4 based bonding material. Suppose if you take up the cascading of multiple radar devices, more than 2 radars. So you need to have a clock synchronization between radar devices. So the clock signal is going to be really high speed, about 20 GHz. So to handle this additional signals, we suggest 8-layer PCB layer stack up, where 2 levels of Rogers is suggested, and then the remaining layers is FR4. What kind of simulation and PCB tools we recommend to design? For antenna design and high-speed interconnects, we suggest to go with use a 3D electromagnetic field simulator. These tools are available from ANSYS and some other companies, and we suggest to go with ANSYS. It gives a good antenna design capabilities and simulation aspects. And for the PCB layer stack up impedance calculation, this is a generally universally used tool. You can go with Polar, the tool called Speed Stack. And for the PCB layout design, any standard PCB layer PCB design tools can be used. Cadence, Allegro, Altium, or Pads. In any other tool, any tool can be used here. There's nothing specific here. When we see the subsystems, what are the different subsystems in a radar chipset? Here we refer to Texas Instruments chipset, wherein this all completely integrated. You have an RF and analog subsystem where you generate the clock source and power amplifier and transmitters, and then you have a receive section. You have a low noise amplifiers, then the mixer, then the ADCs where you digitize the signal, and the radio processor subsystem wherein you configure your ramp generators, or you have the ADC buffers and digital front-end filtering circuitries. They are part of the radio processor subsystem. And the key processor, this is the microcontroller based in a processor, wherein you have the accelerators. Because you are operating at a real high speed, the traditional software, the cycle-based computation FFTs may not be efficient enough. So most of the silicon suppliers, they go with hardware accelerator-based mechanism where FFT, log magnitude, and other accelerators are part of the processing engine. And also they offer DSP inside the same device, wherein you can do the higher levels of applications and development, unfiltering, data filtering, things can be done. And in terms of host connectivity, most of the devices support dual CAN, and you can take the process data through UART. This is the standard connectivity. And we do have SPI connectivity for optional microprocessor interface. And suppose you want to take the pre-processed data, like targets only data, you need FFT processed data or raw data. You can use LVDS data to get the raw data for development purpose. So what is the something about hardware accelerator? So what does hardware accelerator do? It's doing the main function is FFT and windowing of data, and after FFT you do the log magnitude and CFR algorithms to classify the objects. So if you see there, the DMA engine drives the data to the accelerator engine, where the different accelerator functions are performed. The input is formatted the way the computation engine is required. The output is formatted and given back to the buffer where you can do the processing. What kind of data processing? What is the flow of data processing? When you get the ADC data out, you do the initial level of filtering, the unwanted data, DCs are removed. Then we do the range FFT, that is the first one-dimensional FFT with the range information. On the range information is grouped, and we do the two-dimensional FFT for the Doppler shift. And the FFT data are used to do the other data processing algorithms like C4 or log magnitude to find out the objects, and the same buffer is used when you do the 3-dimensional FFT. You can find out the angle of arrival, the angle estimation of the targets, and from this generally you can also take out the raw point cloud data and also the processed cluster the higher level algorithms. When you use the DSPs, you can take out the processed data. So this raw data can be used for if you want to do a higher level of processing, can be used, or you can use that track the target objects for processing. This is a kind of a diagram which shows different type of buffers and kind of data flow and buffers together. So the ADC data, you are getting the ADC data, you are doing the range FFT, and each chip you are getting a range data. It is grouped in bins. Like if you suppose you have 36 chips in a frame, so you have a frame buffer of 36 by 36 frame buffer, and this frame buffer is store the data, store the frame buffer data in L3 buffer. And similarly, you have 4 ADCs, 4 receive channels. So you will have effectively 4 such frame buffers. This the FFT performed data are used to do the data processing algorithms like non-coherent integration, and also amplitude detection, the magnitude detection. Also, you can perform C4 algorithms. So the different algorithms are computed based on the FFT data, and the process data is given to the host or a DSP or microcontroller for the application processing. This is a typical way of explaining the data processing. If you see there, the whole radar is function is performed in a frame. So the frame can have multiple chips. So the active time of a frame is about 10 to 15 milliseconds, where you transmit the chips and process the reflected pulse, and you have a time gap of 25 to 30 milliseconds between the frames. So typically the FFT, when you take a chip, you do perform the FFT, you put the targets in a row like this, and subsequent chips are processed, and the target data are stored in a continuous rows. And when you do 2-dimensional FFT across the chips, you get the Doppler output, the angular, the shift, Doppler shift, or the velocity information. And once you complete your the active chip frame part of the frame, then there's a delay of 30 milliseconds available. This delay time, you perform the Doppler shift, the angular of arrival, angular velocity, angle of arrival, and any other functions like C4 or log magnitude computations performed. So end of the frame should be able to have complete processing is done within the chipset itself. How we estimate the angular resolution? Suppose you use a transmitter, you transmit the signal, and you receive the reflected pulse in a received on single radar, single antenna. With this, you should be able to find the range of the object, but you cannot say what side, it's left side or right side it is present, you cannot detect. Suppose you use the second receive antenna, then the second receive antenna, the target reflected pulse travels additional distance of delta. This gives the additional the travel time gives an angular shift. This angular shift is used to find out whether that object is left side or right side. This gives about 90-degree angle of accuracy. When you use more antennas, receive antennas like 4 antennas, you process the received signals, you get angular accuracy of 30 degrees. Suppose you want to increase your angular resolution, use one more additional transmit antenna near distance of 4D. This, using first antenna, you can get about 4 receive signals you get, and with the second transmit, you get another 4 virtual receive signals. With this, 8 receive signals, we should be get an angular accuracy of 15 degrees. And the third transmit antenna is placed in a vertical shift of D. This third antenna is used to calculate the elevation accuracy. So with this elevation accuracy, you should be able to get about 30 degree elevation resolution. As a summary, if you do FFT on received chips, you will get the range information, and you do a 2-dimensional FFT across received chips, you get velocity information, and you do 3-dimensional FFT across different ADCs, you get the angular resolution. Let's touch upon a little on the test equipments and measuring things. Suppose you want to characterize your transmit antenna, how you design on receive antennas. So you design your transmit antenna, and you can use the lab equipments like arbitrary wave generator and a signal generator, so that you can feed the high frequency inputs to the antenna and get the reflected pulse. The reflected antenna output is fed to a 110 GHz signal analyzer, wherein you can process, remove the carriers and find the target reflected IF signal. The IF is digitized and is given to an oscilloscope to characterize your receive antenna. This is the basic way of calibrating or characterizing your transmit and receive antennas. Suppose if we have designed a product, how to test without any equipments, like closer to use cases, how you test. You need to take this product to a large ground where you don't have much objects. It's a clean, there's no objects there, wherein you place your design under test. And we use corner reflectors. You can see, this is corner reflectors is designed, and this is kept a large distance based on the range what you want to test. So you need to mark the ground in such a way that the range and also the different angles you place your the corner reflectors, and when you do the test, when you transmit and receive, this gives almost 80 to 90% accuracy closer to the use case. When the product is used in a real sense, this is going to be the way you get the reflected pulse and the radar is going to perform. With this, you can do the maximum test, measure the maximum range and the maximum field of view. You can estimate the angular resolution and also the range resolution. Suppose you have multiple objects, you can resolve them and find out what is the range resolution you can get. So what are the offerings Mistral does in this domain? We offer both 60 GHz and 77 GHz areas. In 60 GHz, we offer both antenna on PCB and also antenna on package. Here the antenna is on top of the package, where the whole module size is going to be within 1 inch by 1 inch. This very small module. This module right now we are sampling, and this module is more established. The performance of this radar, the antenna on PCB is good. This is already we are shipping in volumes. And we also offer radar and camera fused together. Radar gives the targets, range, and the velocity information. And a media processor with the camera interface provides the live video. So we superimpose the range, velocity information on a live video, and give you the fuse radar solution. What are the customization offerings Mistral provides? So we also customize the radar modules based on the customer requests, and we also produce in volumes and supply. So we can customize if customer comes with specific size, specific antenna patterns, specific host connectivity and power supply. We customize for them, and we also, based on the use case, we do custom antenna design, and we also simulate and select the right antenna patterns. And we also work on firmware customization and application development. So the application focused areas are hospital environment, or the occupancy detection, or the traffic monitoring. So the multiple areas we help on application development. And this is the fusion radar offerings. So 3-element fusion radar with a media processor, vision analytics processor to detect objects, classifies, annotates the range. So if you see there, you can, this is a use case like you can detect different objects, human or the cars, the range, safe range based on the speed and the range. We can superimpose and provide this data in live video. For more videos, demos, please visit YouTube, where we have more use cases, more demos available from Mistral. And also visit Mistral website for more radars, modules, data sheets, fusion radar data sheets, and different antenna patterns. You get more details. So this ends the presentation. And we'll get into question and answer session. You can raise your hands. We will take it to live Q&A session, and we will invite the participants one by one to answer your questions. So Manfred, I'm taking up your question. The radar and camera data is fused, like applications like where you want to monitor a specific object using camera. Like using camera, you can select specific object like car or human being, and the selected objects range and the velocity will be detected by the radar. Obviously, you are having radar gives the range and velocity information, and the vision processor detects the object, selected objects, and this can be fused together, and you can get many applications like this. And we will contact you directly with more information on this product and your interest. And also we have vision processor on the vision domain. So we will contact you for more details and feed you more information on that. The next question we take up is you talked about in-cabin monitoring, that is ADAS applications. In-cabin monitoring, simple radar can do that. Vision processor may be expensive. So definitely this in-cabin monitoring, the radar module can be used. That 77 GHz radar module can be used. Okay. So we will take up the questions from Giacomo. This is HCL. This is from HCL. How many antenna are available in your offer? We offer 3 transmit antennas and 4 receive antennas. It's a single SoC based design, but different antenna patterns we offer. So if you are specially looking for any cascade design, then we need to customize the design for you. Right now, the current products with the 3 transmit and 4 receive with the different antenna patterns we offer. Yeah. Do you offer? I think this is question from MHD Hitom. Do you offer any cascaded radar products? Right now, we don't have a cascaded radar available with us, but we can customize and provide you a cascaded radar based on the need. Okay, so Manfred asked one more question. Is your AOP 1843 available? Right now, we have sampling 6843 AOP, and we have done some samples for 1843 for specific customer for the SoC company, but right now we offer only 6843 AOP modules. That's the sampling at present, and you will get more modules in Q1 of 2020. But for initial sampling, you can contact us. And other question from Giacomo. Yes, we can offer the services remotely, and we do services for many customers in this area. You can contact us. We offer custom services, and we integrate different microcontrollers to the radar. We offer these services. You can contact us. And the other question is, do you deliver hardware, and what about software offerings? We do offer software customization, and no, we will be happy to offer you the firmware customization and application development. We do these services. Any more questions? You can post your questions to mmWave@mistralsolutions.com. We will answer and come back as soon as possible. And thank you for participating in this webinar. Have a good day and have a good night. Thank you.